in this part of section 5.9, we'll consider steady-state vectors of stochastic matrices. The most interesting aspect of Markov chains is the study of the chain's long-term behavior. We consider the aviary example. Let's go back to the example. Now, along with these assumptions, we constructed a transition matrix as given in this equation. And the Markov chain began with the probability vector here 1, 0, 0. Okay. Now here the question is, what can be said in the example about the bird population in the long run? What happens if the chain starts with other initial vectors? Okay, so we'll check it using computer algorithm. Yeah, this is the transition matrix, and we have two different initial state vectors. P is 1, 0, 0, and another one is 0, 0, 1. This is printout, and now here for P and Q, we multiply T so that each 10 minutes the state vector will be changed starting from two different distributions. Now each time the state vectors are being printed. So we'll see, and after 120 minutes, the probabilities of the birds. In the beginning, we start with for left column 1, 0, 0, and right column 0, 0, 1. Now after 10 minutes, we have P1 or Q1, so that the last one will be in 2 hours. So you can see here now it is changing and looks like converging to a vector. Now, even though we begin with a different initial state, and here later on is converging to the same vector. So that's the observation. If T is a stochastic metric, then a steady state of vector for T is a probability vector Q such that TQ equals Q. Here, if we consider this as a Q, then one more multiplication of T is the same. Once it is convergent, then after multiplication of T, it will be the same. So it is a kind of steady state vector for the transition matrix T. The steady state vector Q can be seen as an eigenvector of T. The corresponding eigenvalue is 1. It's really the form of AX equal lambda x, right? So Q is an eigenvector with eigenvalue 1. Now the question is how to find a steady state vector. And first, we may solve the equation Tx equal x. So that is the same as T minus identity x equals 0. After solving the problem, we choose the Q such that the summation is 1. So that after finding x, we try to divide it by the summation of entries. Then the Q has the the entries and having the summation 1. Okay, let's see this example. This is a transition metric, and the summation is 1, and entries are non-negative. Okay. Now, we want to find a steady state vector for t. Okay. So we have to solve the problem. So we start with a t minus identity. So we subtract 1 along the diagonal, minus 0.4 and 0.3, and that is 0.4 and minus 0.3. And we have to find x such that the metric times x equals 0. Okay. You can solve this problem quite easily. Now, x must be here. Okay, two rules are essentially same. So if you apply elementary row operations for the augmented metric, then you'll get the answer. So here that is. Now change the position and change the sign so that is now 0.3 and 0.4. Or from here we can write here now that is 3 and 4. The summation is 7, so that divided by 7, right? So that will be the final answer. Okay. A stochastic metric T is regular if some metric power Tk contains only strictly positive entries. After a certain number of multiplication of T, once all entries become positive, then we call the given stochastic metric regular. Once it is regular, then here and after the k times later, and it's possible to go from any state to any other stage because every entry is strictly positive. In fact, that is a transition metric, so that from one state to the others, it is moving. So once it's regular, then after k steps, and it is really possible to go to from each state to other states. Okay. See this example. T is given in this way. One of the entries is 0. So at this moment, we don't know if it is regular. And we have to multiply this metric and several times, and then if every entry becomes positive, then we can say it is regular. And find a steady state vector for T using the power method. Because here the eigenvalue, okay, we'll see later on that eigenvalue of the transition metric is always bounded by 1 in modulus, so that once we multiply the transition metric again, then we can find the steady state vector corresponding to the largest eigenvalue, which is 1. Okay, T is given here, and we implement in this metric T, and we try to get T squared and print out. And now we try to apply power method. Just apply T again 20 times. And for T squared, we have this metric. So every entry is now positive. So the given metric T is regular. Now let's see the result of the power method. And after one multiplication, and now here 2, 3, 4, and then finally we have 20 multiplication. We have the result. From somewhere, it's not changing apparently, so that it is convergent up to the 5 decimal point accuracy. Now that is the steady state vector corresponding to the largest eigenvalue 1, right? So we found that by using the power method. Here we have a theorem. T is an n by n regular stochastic metric. Here for the theory we need this regularity. Then T has a unique steady state vector Q. The entries of Q are strictly positive. And the steady state vector can be obtained by using the power method. Start from any initial probability vector. That means that any choice is okay as far as the entries of x0 is non-negative and sum is 1. Then starting from that, here by using the power method we can get the steady state vector. From the theorem we can observe these remarks. T is a regular stochastic metric. Then here, if we consider an eigenvalue, then the eigenvalue must be bounded by 1 in modulus. From this power method, we can see that the largest eigenvalue is 1, just 1, and not in its absolute value. In fact, the number 1 is the largest eigenvalue. But this one is always true for every stochastic metric. I'll prove this one in somewhere in appendix. Every column of TK and converges to Q, the steady state of the vector, as K approaches infinity, which means that TK, the power of T, will converge here the same column Q. Q is the steady state vector. Here we say that the Q is unique, and also entries of Q are strictly positive. See this example, and a stochastic matrix given in this way. Now we want to find the steady state vector Q by deriving the reduced echelon form and try to find the 10th power of T and 20th power of T. Okay, now we'll try to use the strategy. Where is that? Okay, we'll go back. Okay, that one. And we first solve this one and then try to normalize. Okay. Now, so for this problem, now, okay, here, for the first part, we try to formulate a T minus identity and try to get the reduced echelon form. And we multiply for the identity and T and save over there, so that after K iteration, it'll become TK. Right? Okay, let's see the results. Okay, that is reduced echelon form. Now that is x1, x2 are basic variables, and x3 is the free variable. So that means that here x1 equal 6x3, the first row, and second row means x2 equal, oops, okay, that one is 3, okay, 3, x3, and x2 is same as 6x3, and x3 is a free variable, so we have x3. From here, now x is, okay, that is 3 and 6 and 1, along with x3, the free variable. Now we'll try to make the length 1 in summation, so that the summation is 10, so that we can choose x3 to be 1 over 10. So divided by 10. So eventually we can write here that is 0.23, 0.21, and 0.2. Okay, 6 and 0.1. So that is the steady state vector. Okay. Now this portion is the printout from this product. We try to get the power of t, and 10th power is given in this way, and 20th power, we can see that each column is the same as the steady state vector. So that theory is correct. That one, every column of tk converges to the unique steady state vector. Okay. Now we have true or false problems. T is a stochastic metric. Okay. The steady state vector is an eigenvector of T. Is it true? Yeah, it is an eigenvector corresponding to the eigenvalue 1, so it is true. Every eigenvector of T is a steady state vector. Is it true? Not really. Once the eigenvalue is less than 1, then it's not really a steady state vector, right? The all ones vector is an eigenvector of T transpose. Is it true? It must be. Now, T transpose is now given in this way, but now that one is each row has sum 1, because originally T has the column sum 1 for each column, so T transpose has row sum 1. Now all one's vector is just every one. If we make a product, then this one makes here the summation of these entries, which is 1. Again, summation of the entry, there'll be again 1, so that eventually the all ones vector. So all ones vector is an eigenvector of T transpose. So it is true. The number 2 can be an eigenvalue of T or T transpose. Is it true? It's false. First of all, for eigenvalues of T, the maximum eigenvalue is 1. Now, for T transpose, the eigenvalues must be the same. Their eigenvectors can be different. However, and T or T transpose, the stochastic equations are the same, so that these two matrices should have exactly the same eigenvalues. the maximum eigenvalue of t is 1. So the maximum eigenvalues of this one is also 1. So 2 cannot be an eigenvalue of either one. So it is wrong. False statement. All stochastic matrices are regular. Is it true? It is false. For example, the identity metric is a stochastic metric because each column sum is 1 and every entry is non-negative. However, if you make power of identity metric, then always identity metric. Never go to a metric which has all positive entries. So the statement is wrong. Okay, this is the end of the section. Thank you.